Right, well, let's make a start. So, good evening, everyone. I'm David James, and I'd like to welcome you to this lecture from the Institution of Engineering and Technology, the Sussex Network. Okay, to tonight. Now, you know, time is a funny thing. According to the author of Order of Time, Carlo Rovelli, time is really just a set of events, and we perceive the flow of time due to our ability to remember events and project into the future. Well, in spite of that, it doesn't remove the need to measure its passing. And so it's my great pleasure to introduce our guest speaker, Leon Lobo. Leo obtained both his Bachelor of Engineering and his doctorate from Loughborough University, and then spent 10 years working on the development of laser optics. However, in 2011, he joined the National Physical Laboratory in Teddington to the southwest of London. And since July 2019 has been head of the National Timing Centre. He focuses on identifying and developing key opportunities for the time and frequency group, a group that seems to me to be responsible for pretty much everything to do with time in the UK. So what is a nanosecond between friends? Okay, over to you, Leon.
Thank you very much, David. I'm just going to share my screen, and hopefully you should all see that now. Has that come up? Oh.
Yep, that's fine.
Excellent. Yeah, so today I'll be talking to you a little bit about what has been happening in the world of time. It's quite considerable to that extent, not just from the science perspective, but also from a global perspective, particularly around resilience. The talk is entitled, What's a Nanosecond Between Friends? But in this crisis, really, we're looking at potentially going for something along the lines of 6.7 nanoseconds between friends. And I'm sure you'll work that out. But yes, so I'm based at the National Physical Laboratory, which is the UK's National Measurement Institute. We're based in Teddington. And our driver really is around impact from science. So we manage the primary standards in the UK and provide traceability to the SI and disseminate that to the UK towards prosperity and quality of life, basically. We were established in 1900 and have been developing a whole range of technologies and standards ever since. Today, we'll just concentrate on the element of time. So we've got about 400 labs on site. Many of you may have already visited, but it's quite an extensive capability for the UK as a government lab. We've got about 1,000 plus staff now, of which around 550 plus are scientists and engineers working across the board from the challenges of today. But for this talk, I'm going to concentrate on this element. So we are the home of the UK's timescale, which is UDC NPL, the national timescale, UDC being Coordinated Universal Time. And we manage that and disseminate that to the UK. But we do a lot more around the time area, as I'll talk you through. So the question really is why is time important? Across the board, across sectors, timing plays a significant role, either directly, whether it's phase synchronization of the power grid, synchronization of networks, or whether it feeds into the likes of position navigation and timing solutions like global navigation satellite systems like GPS and Galileo, etc. We've got it's embedded within our digital infrastructure. And that's equally a huge benefit, but also a huge vulnerability because of that dependency. And I'll be running through some of the elements around that resiliency aspect that is being developed, not just at the NPL, but across the UK, within government and globally, for that matter. So in the telecom sector, for example, we've got a huge range of networks, whether they are fixed line or mobile systems, and that's extending into new generation of technologies based on 5G and beyond. Synchronization of that capability is incredibly important for that to operate. Whether it is the timing systems providing the source of timing to the network, the systems delivering to the base stations, the synchronization of the base stations, and as users, effectively, all we really care about is that our phone is operating as we expect it to. And particularly now in this new digital way of working, I mean, the last IET meeting that I presented at was in person in London, and pretty much every conference and event is digital now as a webinar, and is likely to be a hybrid event moving forward. But we are entirely dependent on our Wi-Fi systems, our network capability, and our mobile systems in order to operate this. And that's only going to be extended further as 5G develops, and you have a whole new range of applications emerging because of the increased bandwidth, the increased lower latencies, but also the higher capacities that it'll enable. And it's all reliant on timing. When you move on to the likes of transport and emergency services, transport, of course, has been one of the oldest areas where timing was important, because it all actually started, in fact, from knowing what time your train was arriving. And in fact, that led to the element of unification of and creation of time zones, as well as how time is managed and operated today. But more importantly now is that element around global navigation satellite systems that rely on time to operate and to provide you with that positioning piece, whether it's for the emergency services or for maritime users or aviation from that standpoint. The energy grid, again, it's all about phase synchronization and phase of measurement units, looking at essentially ensuring that the grid operates as we expect it to, but also as more and more renewables are feeding the grid, we need to make sure that it can be synchronized so that nothing goes bang effectively. And in fact, some of the timing requirements are approaching the microsecond and well into the nanoseconds as that capability increases. But the energy sector also uses timing for defect detection, as a time of flight measurement capability. And this requirement is only going to increase as we develop better technologies in the future. Moving to food and agriculture and logistics and that just-in-time supply chain, the element of precision agriculture, the element of that transport capability and getting your supplies to you, whether it's to a supermarket of your choice or to your home, is very, very dependent on positioning and navigation. And again, that is all dependent on timing. So the time signal, so in fact, GPS constellations, Galileo constellations are based around time being sent up to the satellites and those signals sent down to your receiver that works out the time difference of arrival, trilaterates its position, and tells you where you are on the surface of the Earth. The better the timing, the better the positioning capability. And in fact, precision agriculture were one of the early adopters of the technology and started to use differential GNSS solutions to get very, very accurate positioning in order to harvest crops, but also, and that is developing very, very rapidly on that front. Across the board, as you'll notice, there is a huge emphasis on the reliance on GNSS and those technologies. And there's an element of how we start to make that more resilient. The finance sector is an interesting one, actually. When I first joined NPL, we started to engage with the finance sector. I never really thought that they'd be operating at a level that required high precision time. But soon came across the whole element of low latency trading, high frequency trading, and the infrastructure that is in place to operate that. And it's incredibly significant. The aspect of regulation has also been very important in providing market clarity and being able to ensure that there's an element of regulatory forensics in the event that there's a crash or any anomaly within the market. One of these, just to give you some an idea of what these figures are worth. So there was an incident with Thomson Reuters, which is in the public domain, where they put out a news feed that automatic systems could trade on based on the symbols that were sent out. And they put out this news feed about 15 milliseconds earlier than they should have. And $28 million was traded in that 15 milliseconds. There have been flash crashes, and understanding who did what and when is incredibly important moving forward. The regulatory environment now is that MiFID II, which is Markets in Financial Instruments Directive, which kicked in a few years ago. It requires that all timestamps for all reportable events have an accuracy and traceability to UTC at the 100 microsecond level for high frequency trading and at the millisecond level for electronic trading. And that's quite significant because it's the first time in Europe that there's a regulatory requirement for timing in the finance sector. I'm just going to show you a very quick clip of a single stock that was traded globally as a high frequency trading activity. And you'll get an idea of how fast these systems trade. It's a very short video. Now this came from a company called Nanex, and it's a Johnson & Johnson stock that was traded. And you can see how fast high frequency trading systems operate. There's a whole element of co-location where the systems that conduct the trades operate very, very close to the matching engine that is the stock exchange. And it's really about who gets there first. And the element of latency plays a huge part in the finance sector on that front. There's a big race to zero to operate at that level. But emerging needs, whether it's smart cities, the Internet of Things, and 5G and beyond, is significant from the point of view of the element of resiliency for timing, but also the performance level. And it's going to be an area that's going to emerge from the point of view of the standards environment, the regulatory environment, in order to operate not just within locales, but globally for that matter. Autonomous vehicles is another key area where there's a lot going on and a lot of systems being developed and tested. But one of the key dependencies there is GNSS. So We know about the systems on the car, which use LiDAR and radar and ultrasonic sensors. It's all time-of-flight-based solutions where timing is important. But the positioning itself is, again, GNSS-based. And one of the key things around the roadside infrastructure is about timing to those systems and how that is, those comm systems and how data is transferred between the vehicle and the infrastructure is going to be important, not only from a performance perspective, but to ensure that it is resilient moving forward. There are elements around legal provenance and cybersecurity, where as transactions get conducted, the timestamps that are applied need to have an element of provenance in itself. So the traceability back to the global timescale needs to be demonstrated in order to operate and to ensure that you have confidence in that data. And similarly, it's about that security and resiliency of our systems. So the future functional requirements is all about increased accuracy and traceability, the element of stability of timing systems within a system itself, but better synchronization, lower latencies, increased bandwidth, spectrum allocation, and how we manage that and increase that capacity by having better control of the spectrum and of how we communicate. But the security and resiliency across the board is a key factor that is developing very rapidly as well. And it's all supported by that metrology underpinning. Back at NPL, that's what we do. That's our bread and butter, to support the economy, to support these technology advances, to provide that confidence in what is being commercially developed and delivered is what it says it is, but also how we can actually support the next generation as well. And it's all about that assured capability, where we can actually have that level of confidence in systems. So what are the challenges? So in our new normal, as I mentioned, we are increasingly dependent on a rapidly evolving digital infrastructure. I mean, the next failure, currently it's a biological virus. The next one could be a digital one. That dependency needs to be matched with an element of resilience so that we can operate as we are over the next decade and more, in a way that we have confidence in what we have as in terms of data, but how that data gets transferred across the globe as well. And that's really in response to that evolving threat landscape and the threat vectors, whether it's for GNSS or networks and the cyber threat. And of course, we talked about the emerging application base. But there are a whole range of alternative technologies being considered, whether it's for positioning, navigation, or timing, and to secure that critical infrastructure across the UK and beyond. So PNT, it's an acronym that many of you would have heard. The element of timing particularly tends to get lost because it's effectively an invisible utility to that extent, whether it's you get it from GNSS or whether you get it over the network or over your mobile systems. Now, when you look at the critical national infrastructure sectors, the 13 sectors as we have it in the UK, there is a huge dependency of position, navigation, and timing, particularly from satellite systems. But more importantly, is the huge interdependency of these sectors. And so regardless of what the sector is, it is almost very, very dependent on the likes of transport or comms or financial systems. And it is that interdependency and the dependency on those critical sectors which have that need for position, navigation, and time that we need to look at to secure and make much more resilient moving forward. Now, this was highlighted in a couple of documents over the past few years. One was the London Economics report that effectively highlighted that if we lost GNSS, it would cost the UK economy £1 billion a day. That was an underestimate. That's been revised and reconsidered to understand what it is now. The other document that's worth having a look at is the Blackett report on satellite dependencies for position and time. And what that raised really was, not only is the UK heavily dependent on GNSS for position, navigation, and time, but that there is an incredible lack of awareness of the dependency. And that is something that really we need to consider for pretty much everything we do and the systems we implement, to understand what that dependency is way down in the stack and to ensure that we can make that much more secure. When we look at some of the vulnerabilities and the threat, it's quite multifaceted, whether it is things like denial of service and jamming, or spoofing, where you could fool the receiver into thinking it's got another time and essentially deriving a different position. Whether it's meaconing, where essentially to rebroadcast from a local receiver, intentional or malicious. But then the elements of the cyber, the physical attacks, and human error. I mean, we've seen cases where all due diligence is done around understanding latencies in a GNSS system, from the receiver down to the from the antenna down to the receiver, and then simple things like the offset to UTCs is implemented with the wrong sign, effectively doubling the error. And you can't really tell because you still have a time that the receiver is providing, but it's very, very wrong. And the only way you can actually understand that error is by comparing it to a reference. You also have the elements of space weather, where ionospheric effects can, at least atmospheric effects, and space weather, where you're looking at solar storms potentially disrupting the signals in space, but also taking out the satellites potentially. And the space segment itself, we've had cases in the past where clocks have failed. This is on the Galileo constellation, for example, or wrong data was provided to the space segment, and essentially all the systems on the ground had significant errors because of it. When you look at the National Risk Register, the pandemic is right up there, and this is the 2017 one. So it was certainly something that was planned for. But if you look further down, we definitely have space weather. And one of the things that is being considered for the next iteration is the element of other vulnerabilities and threat, like the jamming and the spoofing effects that are being seen much, much more regularly now. So time as that invisible utility tends to fall in between the cyber and the physical. And to that extent, it is very, very much an invisible utility. It's a free signal available as a space signal from GNSS and embedded across the digital infrastructure. It's assumed to be there till it's not, and that's where it becomes a problem. And there are some sectors, as you can see, which have critical dependencies on time. What we're doing at the NPL is looking at underpinning that by providing a resilient capability in order to support not just over the networks, but potentially over terrestrial broadcasts as they develop in the UK and beyond as well. So how is time generated? So the SI unit, the second, is defined by a Cesium-133 atom. It's the hyperfine transition in the ground state of cesium. And it's a microwave frequency, so about 9.2 gigahertz effectively, that is used to determine what that second is. Now, the way the global timescale is generated it's, as the name suggests, it's a coordinated affair. So you're looking at about 80 timing labs across the globe contributing data to generate what becomes a paper timescale effectively, that is UTC. The real-time realizations of the global timescale are the national labs that contribute to that formulation process. So the way that works is we submit data from the clocks at NPL, and similarly other labs do the same on a daily basis, typically for many of the labs. And what that creates is basically a weighted average from around 400 clocks globally that creates something called free atomic time. Now that becomes international atomic time when we use our primary frequency standards that are Cesium Fountains, which realize the SI second and lock down what duration in time is a second in that free atomic time scale to create international atomic time. Now that only becomes UTC once we understand what the Earth is doing in terms of how it's rotating, because it's wobbling and it's slowing down. And there's an organization called the International Earth Rotation and Reference System Service that essentially is monitoring the Earth. And essentially, if the mean solar day diverges from atomic time, because atomic time is a much, much more stable time scale, by more than 0.9 of a second, a leap second is added or taken away. And based on that, we get UTC. Now it's a process that takes some time to calculate. So what happens then is the offsets of each of the national labs or each of the national timescales from that paper timescale is provided as a bulletin or as a report, effectively called circular T, back to the labs. And then we have the option to either slowly steer our timescale to that paper timescale or maintain the offset and inform the nation of the offset. The tier one labs like NPL, like the NIST in the US, PDB in Germany, and several others tend to be within a few nanoseconds of that paper timescale. So we tend to slowly steer our timescales to UTC and then essentially provide that offset as required. So at NPL, beyond the timescale generation, we have a huge group. We've got about 50 plus scientists and engineers working purely in this area of time and frequency, with about 20 visiting scientists and researchers and students effectively working on a huge multitude of different things. We've got 3 distinct groups within this time and frequency department, looking at things like optical frequency metrology, where it is the next generation of optical clocks. Remember, the second is defined by a microwave transition in cesium atom. The next generation of clocks will be optical. And things, technologies like frequency combs that allow us to actually measure these optical clocks and compare them with other clocks. But also things like fiber transfer of very, very stable frequencies in order to compare the clocks. Because if you consider that if the second and the primary standard is based on a microwave transition, and the next generation of clocks are already better than the current definition of the second, the realization of the second by virtue of these cesium fountains, how do we know that? And the only way to do that is to compare optical clocks in different labs across Europe and beyond. And so we have to develop all the underpinning technologies, not just to be able to create these new optical clocks, but also to transfer these stable signals at stabilities better than the clocks themselves. We've got a group that is concentrating on compact clocks, as well as things like clock components and atomic sensors. Because in addition to the high-end clocks for the next generation of the global timescale and the potential redefinition of the second by an optical transition, we are also considering how clocks for commercial users, how those ought to start to iterate. So it's clocks for, as I say, for telecom base stations and primary references into telecom networks, or whether it's for financial trading systems and beyond, or for GNSS and space clock technologies as well. And then, of course, we've got a group that's concentrating on the national timescale, contributing to UTC formulation, but also considering what is the next generation of that, as well as delivering services into the various sectors. I'm going to very rapidly go through some of this capability. So we've got a whole range of atomic clocks at NPL that contribute to the timescale. It's based on commercial cesium clocks, hydrogen masers, and our Cesium Fountains. But we're also, as I say, developing the next generation of optical atomic clocks, which are based on strontium and ytterbium. Now, the Cesium Fountain that we operate, we've got a few of them, and we've also provided them to other national labs, operate at the parts in 10 to the 16 uncertainty. And you're looking at about 20 picoseconds per day in terms of drift characteristic. So it's quite a significant capability. With the optical clocks, we are moving into the part in 10 to the 17 and beyond. So they are much, much better already than the Cesium clock capability that we have within the fountains. The underpinning technologies, whether it is femtosecond combs, and the capability there extends into the part in 10 to the 21, whereby we use multiple combs to compare and understand how these femtosecond combs and that technology can operate at its limit to support clock comparisons. But also the lasers, the stable laser systems that feed these clock developments have to be at a significant level of capability. And in fact, we are developing reference cavities based on ultra low expansivity glass to generate stable lasers and stable laser wavelengths, which are not just very, very stable. I mean, you're looking at the hertz level of line widths at the gigahertz and the terahertz range. So it's actually at the hundreds of terahertz. But we're also developing these for space applications. So to be able to survive launch and operation in space. And to that extent, we've got to make them incredibly vibration insensitive. The other element that I mentioned, some of the fiber transfer capabilities, and those are also progressing significantly. And I'll go through some of those in a sec as well. And the miniature clocks, whether it is based on cesium or ytterbium ion, and then potentially some of the transportable optical clock technologies as well. Mentioned some of the cone technologies which support optical clock measurements. And we're also developing things like microcombs, which allow those low size, weight, and power capability for future optical clocks. We also support the likes of the telecom sector by providing frequency standards in order to measure and underpin some of the systems in that sector as well, whether it's by iodine stabilized or acetylene stabilized lasers that we manage and operate at NPL. Now, in order to compare our microwave clocks to our optical clocks and understand how well the optical clocks are doing against the Cesium Fountain, we use these femtosecond combs. effectively, they allow us to either compare clocks at different wavelengths or generate microwaves by beating multiple frequencies to create things like universal synthesizers, where essentially you can lock a particular frequency to a standard, like the Cesium Fountain or to a hydrogen maser, and then pick off another frequency further down and essentially use that, which has the same stability as a source, to compare to another species. And that capability is quite significant. And we can also transfer that over fiber in order to compare remotely, which is, it's a capability required in order to look at clocks in different locations. So how is time disseminated? So we generate the national time scale. We can transport clocks, and the earliest examples of that were Ruth Belville in the City of London going to the Greenwich Observatory, taking her stopwatch, setting the time, and then selling the time across the City of London. But we've moved on quite significantly from that. Whether it's low frequency signals like MSF, which is the radio broadcast, or over the internet, over network time protocol. But we also have services that we're now delivering over fiber, for example. The NPL time service being one of those which we deliver to the financial sector. With fiber transfers, of course, cost is a significant hurdle there, particularly if you're using dark fiber to do that. And there's a huge drive globally to start to understand how we could develop better and protocols to deliver over essentially the internet in some cases. And there's already some work being done around transportable optical clocks to do that. So the NPL time service that we have, which is one of the first services over a fiber network, essentially delivers time to the financial sector for high frequency trading and regulatory compliance, but does it in a different way to all the broadcast services, in that we're actually monitoring what comes out at the far end for the end user, and essentially providing that time with service levels for accuracy, with traceability to UTC, as well as availability metrics and certification, so that when a market participant, whether it's a bank or a stock exchange, needs to demonstrate to the regulator that their timestamps are compliant to regulation, they can demonstrate that traceability chain all the way back to UTC. And it's a far cry from what we used to do. So back in the day, organizations used to send us their clock mechanisms to certify. So that certificate there from 1915 was the first Rolex wristwatch that was classed as or certified at the NPL as a Class A instrument. What we do now is we deliver the time with that certification. So the certificate on the right is the sort of service that we provide to the financial sector now. And regarding clock comparisons, the optical clock comparisons, as I mentioned before, we have networks going into Europe, comparing our optical clocks between NPL and the French, the Italians, and the German labs, and that network is extending even further. And that capability is quite significant. When you're transferring very, very stable frequencies over these networks, you've got to take into account diurnal effects, because the stretch of the fiber itself, but also vibrational effects, so transient effects. And so we have active compensation on the links. But it's that virtue of being able to essentially have to control the environment in order to transfer the frequencies actually led us to new discoveries. So one of the things that we picked up in 2016 was some noise on the signal that we had on a fiber just between Teddington and Reading. And it turned out that we were starting to detect earthquakes as far afield as New Zealand and Japan. So it's quite a significant capability when you consider the networks, the fiber networks that are wrapped around the globe as it stands for transferring data, and what we could do with that as a seismic detection system for the globe. An early detection system that will allow us, particularly for undersea networks and earthquakes in the oceans. That is a capability that we are starting to develop and understand better in order to put those monitoring systems in place. We also use GNSS to transfer time, as well as satellite communication systems. So as a two-way satellite time and frequency transfer capability between clocks. And those tend to be how we transfer time between labs for UDC formulation purposes, as well as comparing timescales. And that's an international effort, so we do that on a regular basis. So what does the future look like for time? We talked about some of the high dependencies around GNSS. We talked about the blacket, but and the limitations around some of the technologies that we have for dissemination, whether it is time over the internet or even GNSS for that matter. When we look at the timescale generation and management, UDC NPL, we're based in Teddington. As it stands, as a single site managing the national timescale, we are a single point of failure. And moving forward, particularly as that dissemination of resilient time from the point of view of alternative timing dissemination techniques, it is more and more important to secure that capability for our digital infrastructure. And so there's a lot of work being conducted around that front. So there are two primary areas that I'd just like to touch on. One is around the science capability, so improving performance of the clocks, the redefinition or the potential redefinition of the second with the next generation of optical clocks and that optical transition, but also the element of increasing resiliency of what we have in place now, and also improving access to all these new applications, providing alternative means of timing for capability across the board. So from the point of view of improving performance, we took the first accurate atomic clock was actually developed at NPL back in 1955. If you want to see it, it's in the Science Museum now. That was developed by Louis Essen and Jack Parry back in 55 at NPL. And that was accurate to about the second in 300 years. That's rapidly developed. So we've been essentially that capability is improving by about the order of magnitude per decade. But all the blue dots that you see are microwave clocks, including the Cesium fountains that are primary frequency standards now that tell us what a second is. The optical clocks have been improving at a much, much steeper rate and have already surpassed those microwave clocks. And so that redefinition is going to be an inevitability moving into the next few years, where we have better stability and better performance from these optical clocks. Already, when we talked about how UDC is formulated, there are already about 4 national labs globally that contribute optical clock data, and currently they have to be contributing as secondary representations and secondary standards. But once we move to that redefinition, there'll be a whole contingent of optical clocks from across the globe contributing as primary standards, not just to increase stability of the timescales and the SI second itself and provide better precision for that, but it essentially will be able to be leveraged within our infrastructures globally. Just moving on to the resiliency piece, a key development in the UK that kicked off about a year ago is the National Timing Centre program that is led by NPL, and we've got a few government partners. That single point of failure that I mentioned before is finally being addressed. We secured about £36 million for this 5-year program to put in place a resilient capability for the UK for our critical national infrastructure moving forward. And what that is, we've got 3 primary objectives for this National Timing Centre program. There's a resiliency objective where we'll be securing what is in place now by creating a geographically distributed UDC NPL in multiple secure locations. We've got an innovation objective, which is really about stimulating the supply chain for timing, time dissemination, frequency dissemination across UK industry. So we'll be providing a large amount of funding to get industry to start to consider their next generation of products and services, to develop new commercial services, to deliver time to the energy sector, the telecom sector, the emerging smart cities and distributed ledger platforms, autonomous vehicle infrastructures and the like. But also to underpin that, we also have a skills objective where we're looking at assessing and addressing the skills gap across the UK, because all the organizations we've been engaged with have almost unanimously told us that they find it incredibly difficult to recruit the relevant skills in this area. And it's almost always the case where they've got to reskill and upskill their people coming into the organization or people already in the organization. And to that extent, we are looking at how we can address that through creating a whole range of training courses and the like. So from the resiliency objective, currently we submit data as UDC NPL and part of the UDC formulation process to the Bureau of Weights and Measures, which is the BIPM, which is our umbrella organization based in Paris, to create that global timescale that is UTC. And what we'll be doing is putting in place a geographically distributed capability on these multiple secure sites, all meshed up with multiple modalities of dissemination. So leveraging fiber and SATCOM as well as GNSS to transfer time such that we increase resilience of the timescale very, very significantly. In addition to that, and as part of that innovation objective, in order to provide these references to the user segment, we'll be putting in place geographically distributed node capabilities, which won't be contributing to UDC formulation, but will essentially be getting references from that resilient enhanced timescale capability that we're putting in place. And those nodes will provide that innovation and that R&D capability with references for time traceable back to UDC, but also frequency for generation of new products and services, as I mentioned. So over the 5-year program, and we're already a year, well, we're in our 2nd year now, we are designing this capability and we'll be starting to implement that over the next year. But beyond the program, it's all about continuity of operation as an enduring capability for the UK and scalability of the the nodes particularly. So it's about how we reach different sectors, whether it's factories of the future, IoT implementations, the energy grid, etc., and putting these nodes in place where it's required with the capability, the resiliency, the security in order to support that particular application. It's going to be quite a significant delivery. So as I said, the route to resiliency is all about multiple secure sites, multimodal technologies and dissemination. And it's all about having disparate failure modes. So there's no silver bullet solution. It's about leveraging every solution that is available to increase resiliency. From that skills education and training piece, we've created a training blueprint, and we've been looking at a range of different solutions around that front. So whether it is training courses, degree modules, studentships, apprenticeships, etc. And it's a whole wide range of audiences that we are catering to that effect, whether it's very generalist e-learning courses to provide that overarching time and frequency brief, all the way through to very specific industry sector-based courses in order to support developments in that area. So it's a whole range of different things that are being developed and will be starting to be delivered over the next few years in conjunction with industry and academia. From a national perspective, there is a significant drive in the UK government as well as governments globally to secure what is currently capability, but also to ensure that our dependency doesn't entirely rely on one system. So whether it's a space asset or a terrestrial solution. And the driver really is about a system of systems approach. So leveraging all the different technologies to create that resilient infrastructure, that resilient assured capability moving forward. And with the National Timing Center, what we are looking at is providing that underpinning resilient source of time into that system of systems, whether it is for a terrestrial broadcast, space asset, ground segment, network delivery, or whatever it may be. It is about supporting however that system of system develops in the future. Similarly, across the globe, there are a huge range of developments for different reasons. Some of them have been because of denial of service, because of jamming. And so some of the links that have been put in place are primarily because of that. That's the wide area terrestrial broadcast systems based on around ELORAN. But also in Japan, for example, they've been looking at multiple sites for managing their timescale because of earthquakes, for example. In the US, a law was passed and an exec order was signed by Trump earlier on this year around this security and resiliency of time specifically. And the US control and manage the GPS constellation. So it's quite indicative of how important they see it as well around that whole resiliency piece. Then there's the other element of legislation, regulation, and standards. So as our landscape, digital landscape develops with all these new applications that we mentioned before, the element of standards, the element of regulation is going to play a key role, not just to ease adoption, effect interoperability, but it's all about providing confidence to the user that these systems are what they say they are, and they can use them and rely on them moving forward. For example, we talked about the finance sector previously. as I say, it's the first time in Europe that there's been a regulatory requirement for timestamp traceability. And that sort of regulation is only in place in a few areas. So the only markets that have that are the US, Europe, Canada, Australia, and maybe one or two others. But globally, there isn't that common regulatory framework or that element around how time plays a part. And that's particularly important because the financial markets are no longer a local affair. There's trading happening globally, as you saw in the video earlier on. So it's becoming incredibly important that there is some form of unified system. And traceability to that global reference that is UTC is the way forward on that front. And that is being considered at the international level for that. So moving forward, PNT as we know it may just well be power, network, and time, for example, where we have time as a utility delivered to our infrastructure as that assured capability. So it's really important around to ensure that we have that resilient piece before we get to that stage. And there's a lot of effort in getting to that as it stands. And that's it from me. I'm open to questions now. Thank you.
Thank you very much, Leon. That was, well, I found it quite fascinating. And we do have a number of questions. I'll start from the top, and I see there are a few that overlap. So we'll try and combine those. The very first question, in fact, that came in quite early on from Brian McCohen, who says, why is the time signal on DAB radio out of sync with the signal from FM? And which is correct. Probably yes, something that we all noticed.
That's an ongoing thing due to the latency within that infrastructure. And I don't believe that they can get around that purely because of the latency piece. But it's an ongoing dilemma, that one.
Right. Okay, then we have a number of questions that relate to the influence of Brexit and our ejection from the Galileo project. So perhaps you could
that's a very political one. So once we got out of the Galileo program, the element about accessing some of the encrypted services has been one of the problems, because we, not being part of that development, essentially does not allow us to leverage those capabilities moving forward. However, Galileo still has open services, so many of us now already have Galileo receivers, or they will be in place within our mobile phones, etc. So we will still have access to all the open services on that front. It's just things like the public regulated service, which is that encrypted service, which may be problematic moving forward.
And your relationship with the other centers around Europe, is that affected by us?
Not at all. So the amazing thing about the whole UDC formulation process, and including the clock developments, etc., is that is regardless of any political element whatsoever. So that endures regardless. Those relationships are incredibly strong and will continue.
Good. Okay, next question. Oh, actually, Robert Pardy asked a question early on about resilience, and then commented later that he thought you'd answered it. So well done. You you covered that for him. On the face of it, something that may be a simple question from Peter Smith says, "Great presentation. How does my radio-controlled analog clock work?"
So the MSF signal that I mentioned earlier, which is the 60 kilohertz long wave signal, many people know it as rugby time. It moved from the transmit side, moved from rugby probably a few decades ago now. It's being broadcast from Anthon. So we control that signal from NPL and we monitor the signal and steer the clocks that essentially feed the transmit. Essentially, that signal is what your radio-controlled clock receives. And with the MSF signal, you typically can achieve several milliseconds of traceability back to UTC. So it's certainly not viable for financial sector and time-stamping trades or anything like that, but it's perfectly viable for a clock on the wall and general purposes, basically. Okay, it's heavily used. I mean, it's really interesting. Because it's a broadcast signal, we tend not to have a list of users, but we do know some of the users when we have, say, a planned outage for maintenance or something. And if the user segment haven't picked up on those, we do get complaints coming in. And the best example, in fact, that I came across several years ago now was the pigeon racing community that leverage MSF at the start and finish lines to time the race, which was quite an interesting application there.
Okay, well, a question from someone who didn't leave their name, but they say, "This is really interesting, and thank you very much. But could you tell us a little more about the Cesium Fountain, please? Perhaps especially why it's called a fountain."
Okay. So the Cesium Fountain essentially has a vacuum chamber in which we have cesium vapor that we essentially heat up an ampule to create that vapor. That is hit by 6 orthogonal laser beams, which essentially cool down the vapor. So essentially bring it down to near absolute zero temperatures. And then we detune the vertical beams and launch that ball of atoms that have stopped vibrating now through a microwave cavity, a ring microwave cavity that is tuned to approximately that 9.2 gigahertz that I mentioned, which is the definition of the SI second. And it's launched through that and then falls under gravity. It takes a few seconds. And the reason for that is the interaction time with the microwave signal that is in that chamber. That's the fountain bit, effectively. And if that frequency is just right, and it causes an electronic transition in the ground state, what we see with a probe laser beam below the vacuum chamber is that we get fluorescence. And we don't get fluorescence if that frequency isn't right, so we sweep that. And when we do get fluorescence, we lock that frequency. And because of the physics of the cesium atom itself, we then send out that frequency, and that frequency becomes what is essentially the primary frequency standard. So that's the basis of the Cesium Fountain. I hope that answered the question. It's very simplistic overview. There's a lot more to it because it's all about controlling the environment, the magnetic fields, the electrical fields, the temperature, the humidity, etc., in order to achieve that parts in 10 to the 16 level of stability. But that's how it works.
Thank you, Leon. We have a question again from someone who didn't leave their name, but they said, could you revisit the user need for a very accurate frequency source and discuss why inversing the time signal will not meet the need?
Yes, so there are some applications that do require just frequency, and it's the likes of radar, but also when you're looking at things like calibration of instrumentation, or even references provided into instrumentation. And that's typically where stable frequencies are important. But also when you're looking at things like stable lasers feeding where you're looking at a comm system, so 1550, for example, for telecom wavelengths, and ensuring that those systems are operating as they should. It's the microwave or the optical frequencies that feed those systems are critical. The better the stability, the faster you can actually achieve that level of performance that you require. Now, the element of the reciprocal of the time is viable in many instances, but there are, at the higher end particularly, is where the frequency and frequency dissemination is particularly important, especially when you move into the optical clock regime and needing to disseminate just pure stable frequency in order to operate. I hope that's answered the question.
Thank you, Leon. Then Jim Haslam asked, what is the current maturity of low SWAP optical clocks?
Yes, so currently, so low SWAP is low size, weight, and power. The smallest capability currently comes from the US. It's the CSAC devices, which are chip scale atomic clocks, which are, you're looking at something of the order of a few centimeters cube, basically. We're doing a similar, well, there's a similar development in the UK, which is a little bit larger. It's the miniature atomic clocks, the physics packages that were developed at NPL, and we've got industry now commercializing the capability. So Teledyne, E2V are starting to develop these as commercial systems. But you're looking at something along the size of 50 millimeters by 100 millimeters by 50 millimeters, something along those lines. That is entirely viable for rack mount systems, so 19-inch rack mount systems, and for deployment in the field. But those will drop in size, drop in weight and power, and cost. Cost is another big factor that is being considered.
Okay, thank you, Leon. William Morris first of all makes the comment, a very interesting talk on a key topic for the survival and operation of most high-tech systems. But he asks whether the slides will be available after the talk.
I can make them available, yes.
So if you,
I believe there's a video, isn't
yes, right? I was going to comment that we are recording this talk, and that will be posted on the IET Sussex Network website and on our YouTube channel. But Leon, if you're able to provide a PDF export of your slides, then that would be of interest to people, I'm sure. We can post that as well. Alex Wood asks something about seismology. He says, does optical seismology compare, or how does optical seismology compare with traditional seismology?
So from what I've gathered, it is, so I don't have the detail to this one actually, but the key benefits is around leveraging. I believe it operates in the same regime as many of the sensors that are available to date, but it is really about leveraging some of the networks that are already in place. The transoceanic networks particularly, and using those as detection networks is the driver here.
Well, then Alex also goes on to ask a question about international tier 1 timing labs. How are they determined? How many are there? And is there any system of promotion and relegation?
Yeah, so there are about 80 national laboratories that contribute to the global timescale formulation. The clocks that contribute are weighted. So that average that is created towards generation of free atomic time is a weighted average, and that is dependent on how long the clocks have been contributing for and how stable they are. So it is variable across the board. There are some laboratories that have been contributing for a long time, very stable clocks, whereas some tend to contribute in order to maintain a UDC realization and provide that to their nation. So not all of the laboratories are equal on that front. And the top tier labs also conduct a lot of fundamental research, like you've seen that NPL operates at the moment. So it's not just about the timescales, but about looking at the next generation as well.
Thanks, Leon. We have about 4 more questions, I
Sure.
think. Just a couple of comments, if that's all right with you.
Absolutely.
Okay, you've answered a question that Vincent made about miniaturization of clocks, because atomic clocks, because that was something someone else had asked. Chris Sturgeon asks, what constitutes a better definition of the second? What would be the ideal definition of the second?
The move to the optical regime, where you're looking at 5 orders of magnitude higher frequencies, provides increased stability and precision by virtue of that increased frequency. And that is how that's going to pan out in the near future. So it's just a question of what capability, so what species of optical atomic clock, or what species and how it will be operating, is the determining factor moving forward towards that redefinition.
Okay, then Anthony Harris asks, how accurate is the time on my mobile phone or desktop computer?
It should be at the millisecond level at least. So over the network time protocol, which is how it gets disseminated typically, you're looking at several milliseconds of traceability back to UTC. Typically, but you tend to find many cases when that isn't operating as it should, it can be seconds wrong in some cases.
Right. Okay, then a question from Mike Fellows, just 2 more questions as far as I can see. Do you think that the government's acquisition of OneWeb will help towards providing resilient time services for the UK?
So the element of OneWeb as a LEO constellation or low Earth orbit constellation, with the primary driver, I believe, to deliver 5G, could potentially in the future look at time dissemination. And from the NTC perspective particularly, the way we see it is regardless of the modality of dissemination, what we are considering is the source of resilient time for the UK, and to feed any solution, whether, as I say, it's low Earth orbit dissemination or medium Earth orbit, as most of the GNSS constellations are today, or terrestrial broadcast. So it may be something that could be leveraged as it develops.
Thank you. Another question from Alex Wood. How many potentially useful atomic transitions remain to be investigated? And how close are we to reaching the limits of accuracy in a single source?
I think there will always be a drive to do better. So the best optical atomic clocks currently operate at the part in 10 to the 18 have been demonstrated. And there's a concerted effort across the globe to continuously improve that. And as I say, much of that is to do with controlling the environmental effects. So whether it is vibration, electrical fields, magnetic fields, and the like, and all the systematic uncertainties that cause frequency shifts within the system itself are continuously being bettered on a regular basis, basically. So I don't think that will ever stop improving.
Okay, thank you, Leon. Now, Harold Bland has sneaked in an extra question. I noticed just on the end there. He asked, could you explain how you correct for the varying time lags in optical link transmission over long distances?
This is for optical time lags, or maybe this is just a time transfer question. If it is, typically, most of the time transfer techniques over optical fiber are based on protocols. So IEEE, so NTP in itself is based on a time of flight type calculation, where you're looking at a ping to the far end, and you're measuring how long it takes to come back. You're halving that as the latency, and then you can offset the far end by that amount. And similarly, as the protocols that are developing, whether it is NTP or PTP, Precision Time Protocol, which also takes into account the differences in the clocks at both ends, by virtue of that two-way communication, we can monitor the latency and offset at the far end by the latency. And that extends to the next generation of protocols, which is called White Rabbit, for example, that also provides a frequency or a phase sync as well at both ends to achieve the nanosecond level of time transfer or synchronization capability. So almost all these protocols essentially are based around measuring the latency and offsetting by the latency, and so taking account of that.
Excellent, thank you, Leon. Well, we have many comments that have come in that say, thank you so very much, and how interesting that was. Just wanted to say that what an excellent presentation that was. So
thank you very much. There
are many of those, and well, I'd like to sort of reiterate that, to thank you very much on behalf of the IET Sussex Network, on all of our members and audience, for your time this evening, and what has I agree, been a fascinating talk. So please, thank you very much, and please accept our best wishes for the.
Thank you.
So thank you, everyone. I also thank our audience for attending, and I hope you sort of agree with those comments. Certainly, since you've stayed the course, I guess you must have done. As I said, the talk, recording of the talk will be available via our website, and hopefully we'll be able to post a PDF of the slides as well. So thank you, everyone. You don't have to travel home, so I can't say safe travel, but thank you for joining us. And Leon, thank you again very much.
No problem at all. Thank you.
Right. Good night to you.
Bye. Good night.
Night, everyone.